All right, hello again. It's time for the fifth section of chapter 8. We're going to kind of see in this section something called variation functions. And will seem a little bit like a departure from what we've been doing, but the connection here is that an inverse variation is basically like a kind of reciprocal function or a specific kind of rational function. And other than that, we're going to see direct variation and joint variation. So we're going to see three different kinds of variation, and then we'll see some problems where they are combined. All right, so the vocabulary you need to be looking out for are these things: direct variation, the constant of variation, joint variation, inverse variation, and combined variation. So our first one is direct variation. That's our first vocab word. We say that y varies directly as x. The order here is important. Y varies directly as x if there is some non-zero constant k, so that an equation like this equals true. Y is true. Y equals k times x. So notice this is going to be a linear equation. K, this constant here, this number times x, is called the constant of variation. So for example, y equals 3x. This is direct variation. Y varies directly as x. So y equals some constant, some number, times x. If we know that x equals 7, then I can just plug that in and know that y is 21. So any x I plug in here will always be multiplied by 3 to get y. That's called direct variation. So let's look at this example. It says if y varies directly as x, anytime you hear that, you should think y equals kx. And y is negative 15 when x is 5. Okay, so this relationship, this is a given ordered pair. This is going to help me find k, to find my constant. After I do that, I need to figure out what y is when x is equal to 3. This is a pretty straightforward idea. So when I do direct variation, there's actually two ways to go about it. So when I have direct variation, I'm going to have a proportion that's very direct. So y over x has to equal y over x. So my first ordered pair, negative 15 over 5, has to equal my second ordered pair. But I don't know my second y, right? So it's going to equal my second y over 3. Then I just solve that proportion. So I multiply negative 15 times 3, and I multiply 5 times y sub 2. And when I solve, I get negative 45 equals 5 times y sub 2. And when I divide, I get negative 9 equals y sub 2. So when x equals 3, the value of y is negative 9. That's one way to do it. Notice that with this way that we did it, we didn't have to find k, right? If I want to find k, another way that you can do it is to start with your equation. We know that y is negative 15 when x is 5, but we don't know k. So then if I divide both sides by 5, I get negative 3 equals k. And then I would say, all right, that means I now know my equation is y equals negative 3 times x, because now I know what k is. And I want to find y when x equals 3, so I would just plug in 3 for x, and I would get negative 9. So you can choose either way. You can either do the direct variation proportion, which is y1 over x1 equals y2 over x2, or you can use the direct variation kind of general equation to set this up. And you get negative 9 either way. All right, so you guys try this one. You can choose which way you want to do it. The answer here is A, negative 28. And here I show you both ways to do it, with the proportion or with the equation. All right, joint variation. Joint variation is really similar to direct variation because it's kind of all on one level, if we can say it that way. I just have 3 or more variables instead of just 2. So we say y varies jointly as x and z if there is some non-zero constant k, such that this is true. Y equals k times x times z. So this is my joint variation equation. All right, so if I'm going to do joint variation, let me show you how this works. So in this case, suppose y varies jointly as x and z. Find y when x equals 10 and z equals 5 if I know that y equals 12 when x equals 3 and z equals 8. So again, I can use a proportion here. This is the proportion that I use for joint variation. So it's very similar to the direct variation, just that x and z are together, jointly varying. So y1 over x1 z1 equals y2 over x sub 2 z sub 2. Then I plug in what I know. I know that y is 12 when x is 3 and z is 8. So I need to find y when x is 10 and z is 5. So basically we cross multiply and we end up with 24 times y sub 2 equals 600. And when we divide by 24, we get y sub 2 equals 25. So when x equals 10 and z equals 5, y equals 25. Let me go back here for a second. The second way to do that again would be to start with my direct variation equation. You can start with that and solve for k. Then once I know k, I can plug in x is 10 and z is 5, multiply by k, which is 1/2 here, and get 25. So again, either way is acceptable. So you guys try one. Try a joint variation problem. All right, in this case, we end up with 3/5. And again, there are both methods, using the proportion and using the equation. Either one is fine. All right, our third kind of variation in this section is inverse variation. This is the one that also represents a rational function when I solve it for y. So let's look at what this looks like. Y varies inversely as x if there's a non-zero constant k. Remember, that's called my constant of variation, such that x times y equals k. So x and y are my variables. If I multiply them together, I get k. Or another way to say it, and this is when it starts to look like a reciprocal function specifically, y equals k over x. So that idea of inverse, if you think about it, y is kind of in the numerator on this side and x is the denominator on this side. Or if I solve for k, I have x times y. So in this example, x times y equals 2. If I were to solve that for y, I would get y equals 2 over x. And if x is 6, then y equals 2 over 6, which is 1/3. So basically what happens in inverse variation is that x gets bigger, y gets smaller, or vice versa. As y gets smaller, y gets bigger, x gets smaller. Because when I multiply x and y together, they always have to give me the same number, the constant of variation. So let's look at this one. It says r varies inversely as t, and r equals -6 when t equals 2. Find r when t equals -7. So the inverse variation proportion you have to be careful with. Notice my r and my t sub 1 are in opposite fractions, okay? And my r sub 2 and t sub 2 are in opposite fractions. Why? Basically the way that they get this proportion is like this. So I say, well, this would be my first inverse variation, and this would be my second one. But I know that in this situation, k has to be equal, right? So I can set my two inverse variation equations equal to each other, and when I solve them to put them so that they look more like a proportion, I get r sub 1 over t sub 2 equals r sub 2 over t sub 1. So that's how they get that proportion. So again, notice you have to be very careful with plugging it in. It might be helpful to label as you go. So if r equals -6 when t equals 2, we could call that our r1 and t1. We want to find our second r sub 2, when t sub 2 equals -7. So labeling would probably be helpful. So in our r1 we put -6, and then my 2 goes in the opposite fraction in the denominator. I'm solving for r sub 2 when t sub 2 equals -7. Then I cross multiply and solve, and I get 12/7 equals r sub 2. So that's my final answer for that one using the proportion. If I don't want to use the proportion, again, I would go back to the original equation, which is xy equals k, or y equals k over x. So they say, or I guess I should use r and t for this one, sorry. Okay, that looks a little better. So if I know that r is -6 when t is 2, then I know that my k is -12. And then I can say, all right, well, that means that r times t has to equal -12. So I want to find r when t is -7. I divide both sides by -7, and again I get 12/7 just like we did with the other method. So keeping all of that in mind, please try this one. Okay, your answer here should be B, which is 4. And there are both ways to do it, proportion and using the equation. All right, here's an example of where an inverse variation problem could show up in real life. It says the apparent length of an object is inversely proportional, that means varies inversely, to one's distance from the object. Earth is about 93 million miles from the sun. Venus is about 67 million miles from the sun. How much larger would the diameter of the sun appear on Venus than on Earth? So, L1 is going to be the apparent diameter of the sun from Venus, and we'll let D1 be the distance of the sun from Venus, or the distance of Venus from the sun. Then I have to set up variables for the Earth from the sun. So L2 would be the length of the diameter apparently of the sun from the Earth, and D2 will be the distance from the Earth to the sun. Sorry, small technical difficulty. So we're going to let the apparent diameter of the sun from Earth equal 1 unit and the apparent diameter of the sun from Venus equal V. And we're going to relate our values together like this. So we're going to say this is the same as saying L1 over D2 equals L2 over D1. They just didn't rearrange it in like fractions. They basically just had each of these equal to K and then set them equal to each other. So then we're going to plug in what we know. Notice we're just going to do 67 and we're going to say it's in millions. Same with the 93. And then I divide each side by 67 and I say that's about 1.39 since we're looking to talk about how much bigger or how much larger the diameter of the sun would appear on Venus than on Earth. And that means about 1.39 times as large. So you might be wondering, why did we let the diameter of the sun from Earth equal 1 unit? Because notice the question here is not how long is the diameter of the sun, right? It's how much longer does it appear on Venus than on Earth. And on Venus, it looks 1.39 times as long as it does on Earth. We're not sure how long it looks. We just know that from Venus, it would look longer, apparently, than it looks on Earth. All right, try this one. Okay, in this case, you should have gotten D. All right, and here's the work for that one. So I let D1 be the distance of Mars from the sun and D2 be the distance of the Earth from the sun. And I let the apparent length from the Earth be 1 so that I could solve for the apparent length from Mars, right? But we're not solving for the actual length. Remember, we're just comparing. So we're saying length 1, or the length from Mars, would look about 0.65 times the size as it would from Earth. All right, last but not least, combined variation. In this case, you'll see it's combined because we have direct variation and inverse variation in the same problem. So we're saying F varies directly as G and inversely as H. So basically, this is what our equation is looking like. So we're going to set up a proportion for this information. This is what my first equation would look like, right? F varies directly as G and inversely as H, both times, right? Here's my first set of information, my second set of information. So we would solve both of those for K and then set them equal to each other if you're going to set up a proportion. So if you're going to set up a proportion, you solve them both for K because K has to be the same for all of the information in this problem and set them equal. And then we just go ahead and plug in the information that we need, okay? So 5, 3, and 18 go here, 6, -5, and G sub 2 go here because that's what we're solving for. If you remember looking back at this, it says we're finding G when F equals 6 and H equals -5. And then when we cross multiply and solve, we get -540 divided by 15, which is -36. That would be the value of G. All right, last question on this one. Try this. Okay, in this case, you should have gotten 40. All right, and there's the work for both different ways to do that, with the proportion and without it.